Hi, this is Shinchan. So, in the today's tutorial, we will be actually having a look at the intuition behind linear regression. So, one of the examples at the scikit-learn actually shows that how to implement linear regression with just these sum lines. Right? So it does what is that it actually takes the training example with the x data of this and the y labels as this. That is, you have actually two columns with the values of x1 to be 0, 1 and 2 and the x2 values also to be 0, 1 and 2. And then you have the respective y labels to be 0, 1, 2. Means for the training examples, having the values or say two column values of say 0, 0, you have the output to be 0. And same for the 1 and 1, you have the output to be 1. And for the training example of having the values of 2 and 2, you will get the output 2. And at the end, it actually gets us with the coefficients of say 0.5 and 0.5. Now the question actually arises that how we actually got to this stage of 0.5 and 0.5. That's what we are actually going to understand in this particular tutorial. So, what the basic intuition of linear regression is, it actually multiplies some weights with these particular values and then gets some results as the output, which needs to be close to this actual label so that it can further predict for the further examples. Now, what we used to do also is that in addition to these two training examples, we also used to add another column that is actually only containing the values to be 1 for as an intercept. That actually happens in the case when your when your values are to be 0 and 0. So you might choose any of the weights. Anything multiplied with 0 actually comes out to be 0. So to actually break this, we use an intercept that actually breaks this particular situation and gives you some value. And that's why we actually used to add ones in our training examples in addition to those particular columns. That actually serves as the bias. So, in this particular training example, we can actually visualize this as a particular situation of a 3D graph in which x actually corresponds to this particular column, this particular direction corresponds to this particular column, and the third direction is actually your output. Another dimension can also be visualized, which is actually a bias, but we don't use to consider that while actually making the graphs. So, what's the theory behind this particular thing? Now, we actually need to consider mainly that particular formula which actually needs to update the thetas. That's actually having a name of gradient descent. So, what gradient descent actually is? Whenever some thetas are actually used to actually being multiplied with x values and gets us some output, then it actually results in some error. That is, the output it actually creates is actually somewhat away from the real values that are actually 0, 1 and 2. So we used to try to fix those weights in order to get close to the output values. And that's what in a sense is gradient descent. The basic formula for gradient descent is that theta is equal to theta minus alpha by m multiplied with x transpose multiplied with x multiplied by theta minus y. This might seem a bit complex for now, but let's actually break it down into further steps. So what is this particular term is our error. X multiplied by theta is actually your model's prediction. That is, whatever weight you have selected like this, you actually multiply it with theta values and then you get some output. And then when you actually subtract it with actual value, you get the error. And then when you actually multiply it with your x transpose, it actually means that you are actually weighting out the particular error according to the x values. That is, the more the x value, the more it will actually contribute to the error, and the more it needs to be subtracted from the respective theta in order to actually fix it. And we actually subtract it, not add it, to actually go to the opposite direction so that we can in the next time we can actually get close to the value. Right? If we just keep on adding this value, if we will add this value instead of just subtract, we will actually go more further because we will not be actually subtracting the error, means we will not be actually minimizing the error, but in a sense we will be actually adding to the error. So you can visualize in the simple terms in such a way that we are actually going towards the opposite direction of the error, in order to actually minimize the error and in order to actually get more right predictions. So now this all term might be clear to you, that is weighted error in basic sense. And then we have to actually average it out over all training examples. That's why we have also divided by m. M actually means your training examples, and for this case we have only 3. Then we also used to multiply with alpha, because in some cases there might be a case that your thetas might overshoot, means thetas might actually go to the convergence point where you have minimal error, but because of say high change in this, you might overshoot and you might go to different direction of error. For example, or the basic sense, for the basic sense, you might need to actually predict 1, right? You might need to actually predict 1 and you are currently predicting 2, right? So the error actually is, that is your prediction minus the actual output, right? Means 2 minus 1, that's actually 1. But in some cases when you actually don't apply alpha here, then you while in the process of convergence you might actually overshoot and you might reach from 2 to say 1, not from 2 to say 1, but you might reach 2 directly from 2 to say minus 2. So now in this case the error becomes minus 2 plus 1, that's actually minus 1, and that's actually the same error but in opposite direction. That is, now you are actually predicting it in the negative direction, but it's still an error and you are not actually getting the right answer. You might have expected 1, and that's why we actually introduce alpha. Alpha is actually your learning rate, and this actually corresponds to the rate at which you need to converge. That is, if you actually supply some small value like 0.01 or say or more smaller, then you will actually converge to the right value of local optima at a slower rate, and that is actually being decided by the value of alpha. Now, one thing need to be note is that the theta updates are actually simultaneous update. Means all the thetas are actually updated on their respective values of theta while considering their previous state. Means we don't used to do it iteratively, right? There might be problems while we actually do it iteratively. So we actually do it simultaneously by actually looking at the previous state and then converging to the next state. So this is some math, right? That's what is actually behind all the scene. This is actually how you get prediction. This is how you actually get your error term, that is squared error term. This is how you actually calculate that how much far your model is actually predicting from the real outputs, and you actually just differentiate that particular error term and then you use to subtract it from the theta values by multiplying it with alpha and dividing by the number of training examples. Now what you need to do next is that okay, so we will be actually looking at a practical example to actually learn more. So our practical example was actually this, that is, you have 0 0 and the output is 0, then you have 1 1, then output is 1, then you have 2 2 and then output is 2. Now what you will do is that you will just, as I said earlier, you will add one more term in all the error terms, that is actually your bias, and thus your matrix actually comes out to be 1 0 0, 1 1 1 and 1 2 2. 1 will be actually a constant which will be actually added to every training example, and then it will serve as a bias. Now we have to actually start with some theta. So usually we actually start with all zeros, but we can also initialize it randomly in the case of neural networks. Now what we actually used to do, so for the first training example, let's try actually calculating the output. So what is the output? So our thetas are this and our training values, means training example values are this. So 0 multiplied by 1 is actually 0, 0 multiplied by 0 is 0, and 0 multiplied by 0 is 0. So all added together will actually give us 0. That's actually correct for this particular example because we have started with zeros. But for the next training examples, we will multiply 0 with this, 0 with this and 0 with this, add to all together, we will still get 0, which is actually incorrect, and that's actually an error, right? And same for this, we are actually getting 0, but we need to actually get 2, and that's an error. So how to actually calculate error? Here we have calculated all zeros according to our thetas, that is what actually model thinks after looking at the training example X, and then actually tries to predict 0 0 0, but now we need to actually calculate the error, that what it needs to predict and what it is actually predicting. So we will subtract what it needs to predict from what it is actually predicting. So It is actually predicting 0, but it needs to predict 0. So it is 0 minus 0. That's actually error of 0. But for the next training example, it is actually predicting 0, but it needs to predict 1. So 0 minus 1 is actually minus 1. And for the next one, you have to actually predict 2, but you are actually predicting 0. So your 0 minus 2 comes out to be minus 2. So you have got your error terms. That is actually 0, minus 1, and minus 2. Now the next step was, if you remember, that is actually you have to weight out. You have to weight your error according to your x values. That you can think of this way, that how much the values will be greater of x, the more it will actually contribute to error. Means the more the value of x, the more it will be contributing to error. So the more it needs to be subtracted in the next iteration to actually optimize theta. Something like that, as a basic intuition. So what we will do is that we will create a matrix of our x, of our training examples, right? But in transpose way. That's actually the main point to actually consider here. You have transposed your matrix, that is your training examples is this now, right? 1 0 0, 1 1 1, and 1 2 2, and your error terms are this. Now the question actually arises that why have we actually transposed our matrix? Why didn't we actually multiply it directly? In order to, we have done it in this way, in order to actually calculate the weighted error for a particular feature, that is for a particular theta, so that we can actually subtract it from a theta. So if you actually look precisely, then this whole row is actually this whole column, that is your bias column. And same for other things also, that is this whole is actually your for second feature column, and this all respects to your third feature column. So when this whole is actually multiplied by this, it actually gets us some value, and that value is actually corresponding to a particular theta. Remember, to a particular theta. Like this actually value, when we actually multiply this particular thing with this, it actually, okay, let me actually try highlighting. Okay, so when we actually multiply this particular thing with this thing, right, this particular is actually this row is actually representing the column third, and when this is actually multiplying with the respective error terms, then we get actually minus of 5. And now this particular minus 5 actually belongs to only third column. Similarly, when we actually multiply this, which is actually belonging to the second column of feature values, then we actually multiply it with the respective error terms, then we actually get minus 5, which actually belongs to a second column, and that's actually for the third one. And similarly, this when multiplied with this column, then actually we get minus 3, and that respects to theta 0, right? So we, in this way, we actually get different weighted errors corrections for different thetas, right? So these are the corrections of our thetas. Now, so we have actually got the corrections. Now the next step was to actually multiply it with theta and divide by m. Why divide by m? Because we have to actually average out of all the training examples. Here we have 3, and then why we multiply with theta, as you might have remembered, then we have to actually slow down the rate to a particular optimal value, so that we not overshoot to the different direction and still creating the errors. Now so we have actually chosen our theta to be 0.01, and our number of training examples is actually 3. So what we actually get by actually, we will just firstly divide both these, that is 0.01, and that is actually divided by 3, and that is actually coming out to be 0.0033. Now your theta will be actually we will subtract this particular weighted, these are the weighted errors. Now we will be actually multiplying these weighted errors with this value, that is 0.003, that is actually equal to alpha by m, and we will then subtract it from theta. Why subtract? You already know, we want to go to the right direction, and that's why we are actually kind of opposing it, means kind of opposing the errors. That's why we are actually subtracting. Now our initial thetas were actually equal to 0 0 0, and then our alpha by m actually come out to be 0.003. This will be multiplied with all 3, right? And then we will actually be getting something like these values when actually multiplied with this, and then because it is actually subtracting negative, so it will actually become addition, and then we will get something like this value, right? if we keep on doing this, if we keep on just again and again predicting things, these are our new thetas now. With these thetas, if we actually try to predict our outputs, then we will get new values. And for those new values, we will actually try to calculate the error terms, that how much we are actually far away from the real y values. This will be our new error terms. And then from those new errors, we will get new weighted error matrices like this one. And then for those, we will multiply with, again, with this term, we will get new these things. And then we will be adding with this particular theta, that is our current theta, with those new corrections to actually get new thetas. And in this way, we will be actually converging to a particular value after some time. This is the basic and actually means a basic intuition about linear regression and how gradient descent works. But other factors are also considered here, which we will be talking at the end. So firstly, let's actually have a look at a real example which I've implemented in JavaScript. Okay, so I've actually implemented in JavaScript to actually help understand the basic intuition that what actually happens and what have we actually understood so far. So this is our X data say array or vector in JavaScript, which actually consists of all the training examples. We have 3 training examples, and I've actually just already added the constants, and these are the y values according to these 3 training examples, right? And now I have actually started with the thetas to be 000. Now what I have actually created a predict function that actually does what is just multiply the x particular value, that is y, multiply by that particular theta, and then do this for all the x parts and the theta parts to actually add them all and to actually get the result, right? That is your prediction for a particular training example. Now I've actually tried predicting it here, that is you want to actually get the prediction of say 0, 1, 2, that is the third training example, and I have actually passed the thetas. So when I actually run it will actually come out to be 0. So this is the first one which is actually coming out to be 0. So it is actually at the start predicting the third example's value to be 0, because all are actually initialized with 0. And it must actually predict 2 because the real was actually 2. So the next step was that okay, so this actually predict for one value and get prediction was actually a function. Okay, so this is actually just for one training example a function, but we want to actually do it for all the training examples. We are gonna get the prediction. So what I actually have done is actually made a function with the x data. Whole the x data matrix will be actually passed here with the theta values, and then for I will iterate over all the x training examples, and I will get the prediction by using that predict function, and then I will pass it, I will push it into my predicts array, and then I will return it. Then I've actually console log. Okay, CL is actually a function which I actually made below. That's actually console log, does nothing just other than console.log. Okay, so then we are actually printing out those values onto the console, that is actually get predicts and x data and thetas. So here it actually predicts all zeros as we have expected. For all training examples it's actually predicting 0. Then next, what is our next step? To actually calculate the error, right? So we have actually passed the predicts here and the output here. Output are actually just y labels, right? Which we'll be actually passing. So what it actually does is just subtract the y label from the predict function and predictive value which we will be actually passing as a matrix as an array, and then it will actually return all the errors. So here actually console logging the errors, we actually get 0, -1 and -2. You might have understood why, because it is actually predicting 0 and the actually 0, so 0. It is actually predicting 0 but actually is 1. 0 -1 is actually -1, and 0 -2 is -2. And in this way these are the error terms which we have got. Now the third step is actually to get the weighted errors now, right? If you actually understood. Now I've not transposed the matrix, I've not made another function, I've just used the loop in such a way that I can actually traverse in a transpose way. So what I've actually passed is the same x matrix and the error matrix which we have got here, and then what we actually do is that I will actually create an array or say vector that is actually corrections for thetas, and here we will do what is that we will find the weighted error corrections for our particular thetas, and we will actually keep on pushing it into this array, so we actually subtract it later from the actual thetas. Now, I will actually run a loop for say all columns, because the column are actually your features, right? Column actually belongs to your theta values, because columns are the what which are actually multiplied with theta. So we will actually run first loop for the columns here, because I don't want to do transforms, I want to actually do it directly. And then I will make a variable that is total error is equal to 0, so that I can add upon this particular variable, and then I can actually yeah, I can actually just push that particular total error into the correction for thetas later when this actually loop actually ends. Now, uh, for all those training examples, that is x dot length actually means that for all the training examples, right? For all the training examples, remember, training examples are actually, this is one training example, this is next training examples, and this is next training examples, and these particular are the columns 100, something like that. Now, what we are doing is that for all the training examples, you have to multiply what? Multiply for jth column, right? You have to actually multiply, okay, for the jth training example, and for the ith column. That is, at a particular time we are actually considering this particular one column only, and for that particular column only we are actually traversing over all the training examples, that is j training examples, and we are actually multiplying with the respective error which we have got for a training examples, right? Right. So we have actually multiplied this particular term, and what we will be actually doing that is that, okay, where it come? Yeah, we will be multiplying with that, and then we will be actually adding it to the total error, and then we will be actually pushing it in the corrections for thetas. Next, we have actually got the weighted matrix, that is actually corrections for theta. Now what we need to do? Now we need to actually fix our thetas. So here we actually have created another function that actually fix thetas, and here we are passing the alpha value and the m value also, and the theta, that is previous theta values also, and the weighted multiplication also. Now, what weighted multiplication is actually nothing but the matrix, weighted array matrix, which we have calculated so far. So we will actually traverse all the theta values, and then we will be actually just subtracting from the old theta the alpha divided by m. That's actually what we actually studied in theory, that is alpha divided by m, which is actually multiplied with the weighted multiplication term, right? So we have actually calculated the weighted multiplication term already. We will multiply it with the alpha divided by m, and that particular thing is what we had to divide from theta. So nice. We will actually return the updated theta after it. So one thing I actually need to do is actually this. Let me actually try. I need to actually have a look at a second. One second. Okay, there was actually no issue. Okay, yeah, I have actually talked of the simultaneous update also. So this is what we are actually doing. Yeah. So to actually implement the simultaneous update means that we don't need to actually iteratively change the next theta according to the previous theta, but we have to change the particular theta according to its previous states, because according to this particular gradient descent iteration. In simple terms, we actually need to make a copy of the original theta values, and then we have to subtract from those original theta values this particular weighted multiplication multiplied by alpha divided by m, and then we have to actually return this theta. And we don't need to actually do in this way, that we actually are subtracting from theta itself, because if you actually consider three thetas, then once you will actually update theta 0, then if you actually try to actually okay, so just consider it in a simple way, that we need to actually make a copy of the previous theta, so that all the thetas are actually updated irrespective of the other one, right? Yeah, we can actually do it this way. Okay, so next we have actually made this alpha term that's actually of the value of 0.01, and the m is actually the number of the training examples. This is actually got from the x data dot length. X data is actually your training data, so we have actually got it. That's actually equal to 3, and then we have actually passed it to the fixed data function, right? This is actually one time. So after passing it, after actually calling it for the one time, we actually got these particular terms, these ones. Let me actually show you. These ones actually equal to 0.016 and 0.016, and for the bias theta you have 0.01, and that's actually the same as what we have calculated by hand. And now we need to run it for a number of iterations. So how to do that? We can actually use a for loop for the 3000 times, or maybe lesser. It will also converge for the lesser times. Then firstly we have to actually get the prediction by using the get predicts function, pass the x data and the theta values. Then you have to actually get the errors by passing the predictions and the actual y outputs, and then you have to actually get the weighted multiplication by actually multiplying the particular x values transpose with those error terms, and then you will pass the alpha, m and thetas to those and the weighted multiplication which you have calculated in the previous step to the fixed thetas, and it will actually keep on fixing the thetas. And after 3000 iteration, just console.log your theta values, and you will find that for the bias term you are actually getting something 0.0, but for the theta 1 you are actually getting 0.049999, and you are for the theta 2 also you are actually getting 0.04999, and that's actually close to 0.5 and 0.5. These are actually really close. So yeah, we were actually successful at implementing the linear regression of this example. Might be not perfectly, because another things also need to be considered. One important thing which needed to be considered is that you need to normalize your data while actually passing. Then after normalizing, it will be actually converted into the -1 to say 1 type values, which will be actually more useful and will actually help you converge faster. And the next thing what actually need to be considered is that gradient descent is not only the one method that's actually is used to optimize your thetas. Another method actually use the normal equations, which can actually directly calculate your theta values without actually going through a number of iterations like this one. You can also use less iteration, but yeah, you can actually also can directly calculate those theta. But yes, in most of the situations, gradient descent actually works better, really better. In only some situation you might actually get good values by using that normal equation, but yes, mostly preferred is actually gradient descent, and that's why it's actually also used in neural networks. So yeah, that was actually basic concept behind linear regression, and a basic intuitive approach to actually learn linear regression. Thank you for watching and have a nice day.